Okay, so let's talk about calculating delta S, the enthalpy change for a chemical reaction. So remember, we're talking about thermodynamics, and in chapter 9, we did an example of this, calculating enthalpy change for a chemical reaction. So what we're going to be doing here is very similar, except we're looking at what's called the standard entropy instead of the standard enthalpy. So again, remember, delta S is entropy, and we can calculate the entropy change of a reaction using the standard entropy of a substance. And remember, the standard gets that little degree sign. So the standard entropy of a substance is going to look like this. Capital S with a little degree sign after it is the standard entropy. So the standard entropy of a substance is in its standard state. So that's what that superscript degree sign means. So it's for a pure substance. In its standard state, which is 1 atmosphere of pressure and 1 molarity if it's a solution. So either way, you're going to be given these standard entropies for different substances. These would be given to you in the problem, or you would look them up. Just like we did with enthalpy. We were given the standard enthalpies, so then we could calculate the change in enthalpy for a reaction. So you can look these up in your textbook, or they will be given to you in a problem. And the way that we're going to calculate the entropy change is the same way that we calculated the entropy change, the enthalpy change, sorry, these words sound similar, but the formula is the standard entropy change of a reaction equals the sum of the number of moles times the standard entropy of the product minus the sum of the number of moles times the standard entropy of the reactants. Remember what delta means. Delta means change in, literally. And it's always final minus initial, which is why it's products minus reactants. Because if you look at a chemical reaction, I'm just going to say A plus B gives you C plus D. The initial situation, over here are the reactants, and the final over here are the products, which is why whenever you're solving for the change in a chemical reaction, it's always final minus initial. It's always products minus reactants. So if you understand why we're doing things, it's less of memorizing. So change in is always final minus initial, and when you're talking about a chemical reaction, the products are always the final and the reactants are always the initial. So this is exactly the same reaction that you saw in chapter 9 for enthalpy, but instead of delta H and enthalpy, it's delta S and entropy. So let's talk about what entropy is and what the units for entropy are. So we said entropy was an amount of disorder. And entropy, the entropy that we're when we look up the standard entropy for different substances, the unit is going to be in joules per mole Kelvin. Joules per mole Kelvin. So remember, we're going to tie this all together later, but remember the units for enthalpy in chapter 9 were kilojoules per mole. So this has a different unit, and we're going to see why, because we're going to include the temperature, but this is the unit for entropy. Entropy is joules per mole Kelvin. Okay, so I'm going to write out an example of a question and we'll go through it together. So this question says, when wine is exposed to air in the presence of bacteria, the ethyl alcohol is oxidized to acetic acid, which gives you vinegar. This is what happens when you open a bottle of wine and it just sits around for a few weeks. It gets corked. It means your wine goes bad. The reason that wine goes bad is because once you open a bottle of wine and the alcohol in the wine, ethyl alcohol, gets exposed to air, the bacteria that's in the wine causes the ethyl alcohol to be oxidized to acetic acid. Acetic acid is vinegar. So this is the chemical reaction, and we're going to calculate the entropy change for this reaction. So I'm just going to write out the reaction. So ethyl alcohol So that's ethyl alcohol, and I wouldn't expect you to know the names of any of these. That's not the point here. So ethyl alcohol is going to react with oxygen in the air in the presence of some bacteria to produce acetic acid, CH3COOH, plus liquid water. Okay. So what we're going to do is we want to calculate the entropy change at 25 degrees Celsius. So 25 degrees Celsius is important because these standard entropy, I forgot to put temperature, is also 25 degrees Celsius or 298 Kelvin. So these standard entropies that we would look up in the table are all going to be at 25 degrees Celsius. Okay, so you would look this up. It would be given to you in a textbook, or it would say look it up in a table. So I'm just going to write out everything in this reaction over here and list what the standard enthalpies are. Okay, so you would not know these numbers. There would be no way for you to know these numbers. You would look them up. They would be given to you in the problem, or it would refer you to a place to look them up. So these are the standard entropies for each of these substances. Remember, it's also specific to the state. So if you're looking up the standard entropy of liquid water, make sure you choose the standard entropy of liquid water, because solid water and gaseous water would have a different standard entropy. So just make sure you're always paying attention to the sign. So now I'm going to plug it into this equation. So it is products minus reactants. So here are my products. And here are my reactants. Okay. So I'm going to say delta S, the standard entropy change of this reaction equals products, the sum of the number of moles, so I'm going to say 1 mole of the acetic acid, CH3COOH, times, I'm going to put this whole thing in brackets, times the standard entropy, 160 joules per mole Kelvin, plus 1 mole of water, times the entropy, the standard entropy of water, 69.9 joules per mole Kelvin. So that's products. Now it's products minus reactants. I'm going to write the reactants down below just because I've run out of room. So I'm going to make another bracket. So here's my ethyl alcohol, 1 mole of ethyl alcohol, times the standard entropy of 1 mole of ethyl alcohol, plus 1 mole of oxygen times the standard entropy of 1 mole of oxygen, 205 joules per mole Kelvin. So this seems complicated, and it is kind of just tedious putting all of this in, but really all you're doing is you are multiplying the number of moles times the entropy change plus the number of moles times the entropy change for all of the products, and then you're subtracting the same thing, the number of moles times the entropy plus the number of moles times the entropy. So this is the final minus the initial is going to give you the overall entropy change. So when you do this, you should get something like 229.9 joules per Kelvin, because remember it's 1 mole and then this is joules per mole Kelvin, 1 mole joules per mole Kelvin, 1 mole joules per mole Kelvin, 1 mole joules per mole Kelvin. So now your answer, the change for the reaction is just going to be in a unit of joules per Kelvin. So when you do this part, you should get something like 229.9 for the reactants, and then for the products, you should get 229.9 joules per Kelvin. For the reactants, you should get something like 366 joules per Kelvin. So the delta S for the reaction is going to be negative 136 joules per Kelvin. That's the standard entropy change for this reaction. So now let's think if this makes sense. So we see that this is a negative change. So remember, if your delta S is a negative number, that means disorder has decreased. So let's see if that's true. So on this side of the reaction, we have 1 mole of liquid, 1 mole of gas. So we have 2 moles total, 1 liquid, 1 gas. On this side of the reaction, we have 1 mole of liquid, 1 mole of liquid, 2 moles of liquid. So yes, disorder has decreased because the reactants had a mole of gas. Gas is more disordered than liquid. So the reactants were more disordered than the products. So as this chemical reaction happens, we're becoming less disordered. Disorder has decreased, which means your entropy sign should be negative, and it is. It's easy to get confused in these problems. It's easy to miss a sign somewhere. So you should always look at your answer and make sure that the sign that your math is giving you makes sense with what the chemistry is telling you.